Okay, friends, we are going to now get started on multiple regression, which is a very powerful tool to use for generating forecasts. Analysts will use it to estimate earnings per share, for example, or estimate revenues for a company. These are key estimates, key forecasts that an analyst has to make. The objective, of course, is to be having the least amount of error in your forecast. So you're going to understand the tool as well as the assumptions that go behind the tool. So let's get started with multiple regression. As the name suggests, multiple here refers to more than one independent variables. Now, the label independent and dependent is kind of confusing. It is easy to make a mistake. And more importantly, we should recognize that the relationship between these variables, these dependent and independent variable, should not be construed to be that of causality. There is no causality or cause and effect relationship assumed, and therefore the label independent and dependent does not make any sense. We could instead call these independent variables as explanatory variables, and the dependent variable we should call it as explained variable. I generally prefer to use their common form usage variable label, which is simply x and y. So independent variable is x variable and dependent variable is your y variable. All right, so we are seeking to explain the variation in y. So y variable is our variable of interest. That is special. That is the one that I want to really demystify. I want to figure out what makes it move, what makes it vary. If I figure out what makes that variable move, then I will be able to forecast that variable. And that is the main purpose. That is the main objective. So I want to be able to forecast revenues for a company in the next year, or I want to forecast inflation for the next period and so forth. So that is what our objective is, to be able to forecast a variable, and that is your y variable. And your x variable essentially gives you a helping hand in explaining the variation in y, and thereby allowing you to use those x variables in generating a good quality forecast. Now, this is a linear relationship, and as you can see, the equation as illustrated is a linear equation. All right, and the just a notation, just labels. Betas are slope coefficient except for beta 0, which is the intercept term. There is no x variable multiplying that. So you think of it as your y-intercept in a linear equation. So if there was only one x variable, you will have a two-dimensional space. It is easy to visualize. When you have multiple x variables, it is multiple dimension space. It is a little difficult for me to illustrate in a 2D slide. All right, so now just a quick interpretation of p-values. There is no LOS in this reading that gets into interpretation of p-values, or more precisely, hypothesis testing of a single slope coefficient. The p-values that we are looking at is used just for that. That is for hypothesis testing. In fact, if the p-value is less than your level of significance, alpha is nothing other than level of significance, then you reject the null hypothesis. I'll show you an example to see how it is used in practice in just a little bit. But as I said already, there is no LOS assigned to it, so you're not supposedly required to do any hypothesis testing on a single slope coefficient. However, there is a significant amount of discussion about looking at a model, evaluation of a model. And there is a discussion about, which coefficient is significant, which variable is significant. And so this becomes kind of a background information from level 1 that you're expected to know to understand more advanced concepts that are being discussed in this reading. So that is the only reason I'm introducing this p-value concept for you guys. So in this case, there are two x variables, so x1 and x2. We call it PR and YCS. We'll see these labels in a little bit. Right now, this is just a regression output with two x variables, and the p-values that I want to focus on is in the last column. And for x1, the p-value is less than 0.0001. All right. So, you know, if it was less than 0.01, it would be less than 1%. We compare it to alpha. Typically, alpha, or level of significance, is default 5%. But if you really want to be strict, then you can use even 1% level of significance. Now remember, 5% level of significance means 95% confidence. 1% level of significance means 99% confidence. What does that really mean? So in this case, we found out that the coefficient, the slope coefficient for x1 or PR variable is 0.25. Now we are, 1/100% sure that the true value is not 0. That's what the p-value means. So the p-value always compares vis-a-vis the null hypothesis of the slope coefficient is equal to 0. So beta j, I'll just put generic j. So that is your null hypothesis. Beta is equal to 0. So in this case, instead of 0.25 that you get from a sample, what if the true value from the population? Remember, you don't have access to the population. You only have sample. From sample, you got a value of 0.25. But you can't generalize a sample result to the whole population. We recognize that a sample is going to give you an estimate that is subject to certain estimation error. And therefore, key question is, how far from 0 are we? Well, we are, 0.0001 probability, less than that probability that the true value will be 0. So if we are keeping 1% confidence, 1% level of significance, we still say that it is less than 1% chance. It is less than 1/100% chance that the true value is 0. So we are fairly confident it is not 0. Is it 0.25 exactly? We are not sure. It could be 0.24, but it is not 0. That's what these probabilities really mean. Once again, our job, when you're looking at a coefficient, we want to see if it is garbage, meaning it's 0, versus not 0. That's all we are looking at when we talk about statistical significance of a variable. In this case, x1 is statistically significantly different from 0. x2, YCS variable, on the other hand, has 0.62 probability, or 62% chance that it will be equal to 0. Only 38% chance that it will be not 0. Now we want that chance, we want to control that estimation error. We want that chance to be less than 5%. Well, this is obviously not less than 5%. It is 62%, which is obviously more than 5%. And so we say, well, it is close enough to 0. We can't put too much faith in the estimated value of that coefficient to be able to use that variable in our model. All right. So now we are going to talk about a formulation, and this is based on a actual publication, an actual study that was published. So there are basically, we are trying to estimate the y variable being real earnings growth rate. So that's your y variable, the dependent variable, the explained variable. And we want to be able to forecast that. And we are basically using two x variables, the trailing dividend payout ratio and the slope of the yield curve. These are the two variables that is used to forecast or explain the variation in real earnings growth rate. All right, so here is my model. The real earnings growth rate is simply a function of PR, which is your variable 1, and YCS, that's your variable 2, with their corresponding slope coefficients. These need to be estimated. All right, so we use the study, Arnold and Asnes used a sample of 46 observations. We already know there are two x variables. And here is my regression output. So we already saw this output. The coefficient on PR was 0.25, and the coefficient of the yield curve slope is 0.14. We already evaluated that this coefficient is statistically significantly different from 0 versus the next one is not. All right, so now how do I interpret these coefficients? So the first coefficient interpretation is for beta naught. So beta naught is negative 11.6%. Remember, Y variable is the real earnings growth rate. All right, so if X1 and X2 is equal to 0, then Y, the real earnings growth rate, is negative 11.6%. And that is the first interpretation of the intercept term. Now, what about the next one, 0.25? That's the slope coefficient of PR. Well, the interpretation of PR is if my payout ratio, PR, increases by 1%, everything else constant. That is the key point to keep in mind. So everything else constant, then my earnings growth rate, or real earnings growth rate, would increase by 0.25 of 1%, or 1/4%. So that is my, again, all else constant. Similarly, 1% increase in YCS would result in a 0.14% increase in earnings growth rate. Again, both of these coefficients in our regression output are positive, and that is why you see the same direction. Increase in X results in increase in Y, because both these are, again, positive values of the slope coefficient. Now, what are the assumptions behind multiple regression? The first assumption is that the underlying relationship between Y and all these X variables is linear. And that is obvious, very, very obvious assumption. Why? Because if the underlying relationship was not linear, so if not, the first choice is to transform. So you may want to transform the data, either transform the Y variable or transform the X variable, or transform both, so that now the transformed variables will have a linear relationship. So that is one choice. Alternative, use other models. So don't try to fit in a square peg in a round hole. If the relationship is not linear, you force a linear relationship, what happens? Your model is going to be lousy. It's going to have a high estimation error. It will have a high forecast error. You don't want to use that model in generating forecast. So that is the first assumption. That is a linear relationship between X and Y. The second assumption is there is no exact linear relationship among the X variable. So if I take one of the X variable and I can rewrite that X variable as a function, a linear function of other X variable, then it would be a violation of the second assumption. We will call it multicollinearity, and I'm going to defer further discussion on it until we get to that module. So right now, we just assume that we are looking at X variables and you don't want them to be highly correlated. They should not be behaving very similarly. That's the second assumption. The third assumption is expected value of the residual is 0. There is no bias in our model estimation. So the model is not biased or preferring overestimation or underestimation of the Y variable. And our standard ordinary least square approach to estimation of those coefficients ensures that the expected value of the error term is 0. The next one is the variance of the error term is constant. And what that means is over certain periods of time, if the residuals are having high volatility, some other period of time the residuals have low volatility. If that changes, that is when you have what is called as heteroscedasticity in residuals. Now, we will again defer that conversation in a little more detail in a subsequent module. The next one is there is no serial correlation, again, in residuals. And so what it means is every residual for every observation, remember, every observation will have a residual. You have a fitted value, you have the actual value. The difference between the two is your error in estimation, error or residual. And if the residual of one observation is correlated, is related to residual another, meaning it is influenced by it, then there is a problem. Again, we will defer the extra discussion on serial correlation until later. The last one is the error term. The residuals are themselves normally distributed. It's important. Why? Because we are going to rely on hypothesis testing. So two types of hypothesis testing is covered. One is single coefficient test, the t-test, which you did at level 1. There is no coverage of it in level 2. And then the more advanced or more comprehensive test, and that is your f-test. F-test is used for evaluation of the model as a whole, or to evaluate a full model versus a restricted model. And we'll see that again when we get to the f-test. But the assumption again is that the residuals are normally distributed. Let's talk about that last assumption graphically in just a second. So once again, the three violations that we are deferring we'll cover in a lot more detail, and those are multicollinearity, heteroskedasticity, and serial correlation. Those are three assumptions that we're going to spend more time on later on. Now let's talk about the normal distribution of the residual. We can graphically, visually see if the residuals are normally distributed by using what is called as a normal QQ plot. So software packages allow you to do this plotting, where we are basically going to see the residuals plotted in a two-dimensional space. The QQ plot looks something like this, and for our purposes in the exam, it is extremely unlikely to have an interpretation of a QQ plot, but nonetheless see what we can observe here. Now the expectation is that the red line here represents the perfect plot if the residuals are normally distributed. And in this case, the individual residuals, the green dots, do look pretty well behaved. They look like almost on the line. There is a little bit of an outlier. Why do I call it outlier? Remember, under a normal distribution, 90% of the distribution is within plus or minus 1.65 standard deviation, and 95% is within plus or minus 1.96. That's your standard normal distribution, the z values, if you remember. And so these observations probably, remember, it doesn't say that 100% of the distribution is between plus or minus 2 standard deviation, but as a percentage of the total observation, I don't know how many observations are here, but these could potentially be too many away from the mean. So there may be theoretically some outlier, but I don't see a whole lot of concern, at least in this graphical illustration. So that is our coverage of the first introduction to multiple regression. So we are now ready to get into a little more advanced topics on multiple regression, and that will cover in the next module. Keep up the good work.